Okay, let's jump right in. What if all the invisible electronics that power our world, from the power grid all the way down to your phone charger, had their very own intelligent AI copilot? We're talking about creating a perfect digital copy of our hardware, basically a virtual brain that can predict its every single move.
Just think about it for a second. Imagine your EV charger, or hey, even the entire power grid, having a perfect virtual replica of itself running right alongside it. One that's predicting every move, anticipating any changes, and optimizing performance, all in real time. And no, this isn't science fiction. This is the core idea behind what's called a digital twin. And believe me, it's about to completely change how we manage and control energy.
All right, so if we're going to build these AI copilots, we first have to really get our heads around the problem they're trying to solve. And it all comes down to this incredibly high-speed balancing act that's happening deep inside our power systems.
You see, at the absolute heart of our modern world, you've got these things called power electronic systems, or PES for short. Now, these are the true unsung heroes, quietly managing electricity in literally everything. And their whole deal? It's all about speed. We're talking about switching on and off at mind-boggling frequencies, kilohertz, even megahertz, to control the flow of energy with just absolute precision.
Okay, so to control systems this fast, you've got to be able to predict what they're going to do next, right? And that means you have to simulate them. But, and this is a big but, here's the catch. We need to run these super complex simulations in real time, not on a giant supercomputer, but on these small, low-cost edge devices that are sitting right there with the actual hardware. And, well, that has been a massive technical hurdle for a long time. And for years, engineers have been stuck in this really frustrating dilemma. The traditional tools for this, they're called solvers, they force you into this awful trade-off. It's like you can have a simulation that's really accurate, but it's painfully slow. Or you can have one that's fast, but it's so inaccurate it's practically useless. And neither of those options works for real-time control. So the holy grail, the new goal, has been to completely shatter that trade-off, to get speed, accuracy, and efficiency, all running on that cheap edge hardware.
So how do we do it? How do we finally break that trade-off? Well, the first part of the solution is a really clever AI-powered shortcut.
Okay, think of a traditional solver like a slow, old-fashioned assembly line. It's a step-by-step pipeline. At every single tiny moment in time, it has to do all this heavy, complex matrix math just to figure out what happens next. The problem is, it's totally sequential. Step 2 can't start until step 1 is done. This creates a huge traffic jam, a massive bottleneck. And it's especially bad on modern hardware that's designed to do a million things at once, in parallel, not sit there waiting in line.
This is where the Neural Substitute Solver, or NSS, comes in and just smashes that bottleneck. Instead of painfully grinding through all those heavy calculations every single time, the NSS basically says, hey, let's use a lightweight neural network to just predict the answer. It replaces the slow one-at-a-time parts of the process with a smart AI that can do its job all at once, in parallel, which is exactly what that edge hardware is built for.
And the result of this little switch? A mind-blowing 23 times speed up. I mean, let's be clear, that's not just a small improvement. That is a completely revolutionary leap forward.
And get this, it's not just faster, it's also way more efficient. It slashes the hardware resources needed by 60%. So, okay, we've solved for speed and efficiency. Great. But is that the whole story? Is that really enough?
See, having a fast digital copy is a fantastic start, but for it to be actually useful in the real world, it also has to be incredibly accurate. We need a true twin, one that changes and evolves right alongside its physical counterpart.
And this brings us to what's called the sim-to-real problem. It's a huge deal. A simulation might look perfect on a computer, but the real world is, well, it's messy, right? Components get old, temperatures change, things just drift over time. So the big question becomes, how do you make sure your digital twin stays perfectly in sync with reality?
Well, one way is the black box approach. You just throw a ton of data at a neural network and tell it to learn everything from scratch. The problem is, you need mountains of data. And even worse, the AI has no idea about the laws of physics. It could literally predict something that's physically impossible, which is not good. The much smarter approach is what's called a gray box. Instead of starting from zero, you give the AI a massive head start by basically baking the known laws of physics right into its code. Then, the AI has a much easier job. All it has to learn is the gap. The messy, real-world stuff that the perfect physics equations miss.
And this leads us to a solution with a fantastic name, Physics Embedded Neural ODEs, or PENODE for short. The way to think about it is pretty simple. The foundation of the model is the set of physics equations we already know were true. Then we just layer a small, targeted neural network on top, and its only job is to learn what's called the residual, that little bit of difference between the ideal physics model and the messy, complicated real world.
And because the AI doesn't have to waste time learning basic physics, it can be incredibly small. In fact, this PENODE approach cuts the number of neurons needed by a whopping 75%. This doesn't just make the model more efficient, it also makes it way more trustworthy because we can clearly separate what the hard physics is doing from what the AI is just fine-tuning.
Okay, so let's take stock. We now have a digital twin that is both lightning fast and physically accurate. So, now for the really cool part. Let's talk about the ultimate goal, using this twin as an active, hands-on AI co-pilot.
Right. We've built this amazing tool. Now what can we actually do with it? How do we use it to actively control the system and make it better? The answer is a brilliant strategy called Model Predictive Control.
The full fancy name is Cognitive Digital Twin-Based Model Predictive Control, or let's just call it CDTMPC. And the core idea is just fantastic. Instead of relying on a bunch of expensive, slow, physical sensors to know what's going on, the control system just asks the digital twin. The twin essentially becomes a perfect virtual sensor. It's our AI co-pilot, feeding the main controller a flawless, real-time, completely delay-free picture of what's happening.
Just look at the difference here. The old way demanded all these specialized, high-frequency sensors. That meant more money, more things to break, and most importantly, a ton of delay from just collecting and sending the data. The CDMPC approach just flips that whole concept on its head. You're literally replacing expensive hardware with smart software, generating all the information you need right there on the chip, with basically zero delay.
And the real-world result of eliminating that delay? It's just stunning. Look at this. When a sudden change happens, a traditional controller kind of flounders for a bit. It takes it several cycles to get stable again. But our CDTMPC, with its perfect, instantaneous information, it achieves what's called a deadbeat response. It calculates the one perfect move it needs to make, and bam! It hits the new stable state in a single cycle. You literally can't get any better or faster than that. It's the theoretical limit of control.
So we've gone from the core problem to some pretty brilliant solutions. But let's zoom out. Why does any of this really matter in the grand scheme of things?
Well, the implications are absolutely huge. We're talking about creating smarter, more stable power grids that can actually handle the ups and downs of renewable energy. It means much more efficient and faster chargers for our electric vehicles. It means we can have electronics that can diagnose their own problems and even correct for them as they get older. This really is nothing less than a whole new way of designing intelligent, self-aware systems.
There's a line from the original research that just nails this whole shift in thinking. It says, the approach creates a software-as-a-service paradigm. Think about that. We're moving away from a world where performance is limited by the physical hardware you can build to a new world where performance is defined by how smart your software is.
So we've seen how this can totally transform power electronics, but it leaves you with one final massive question, doesn't it? What other invisible systems that run our world? I mean, think about manufacturing, supply chains, even biology. What else could be revolutionized if we gave it its own intelligent, cognitive twin? I think the possibilities there are truly endless.